but learned a lot from one another, and is one of the very rare experts in SLT. He's going to tell us about all you need is relative information.
Thank you, Dan. First of all, thanks to all the organizers for doing such a really good job with this workshop last week and this week. And for all the years I've been doing SLT, I would never imagine this would happen. And I mean in a good way, that I feel like this feels very important, and that not enough attention is in this area. So I'm really glad that this is happening, and I feel like when I was doing SLT back in 2010, 2011, deep learning wasn't that well known yet, but we knew about these neural networks, and that we were saying we need to understand SLT better to understand the deep neural networks. But I think there was just way too much barrier at the time to understand the field. And so I think what Dan and Jesse and Liam and Alexander and Stan and Edmund, all of you, did I miss out someone? Susan, yeah, all of you have done such a good job explaining this last week, and I feel like the entry is a lot easier now. So today I'm going to talk about relative information, or some of you know it as the KL divergence. Okay, and I thought maybe I would just tell you a little bit of my history. It actually started back in 2008, where I think I was on a walk, and I was starting to think at the time computers were coming out in dual cores and quad cores, and I realized that at some point we are going to run out of the number of cores we could fit in a computer, and that we will still be hungry for more computation. And it occurred to me that the problem with chips at the time was that we were separating memory from compute, that you were storing all the memory in one part of the computer, and then you were drawing into the computer, into the chip, and then you would pass it back to memory. And this back and forth was just totally not the way that we think in our brains. That neurons were somehow computing things, but at the same time also storing things. And it's very, very hard to separate the memory component of a neuron from the computational component of a neuron. And at the time, I said, I really wanted to understand this. And I went to Bernd Sternfels, my advisor, and I said, I want to do machine learning. And then he said, I know of this Japanese statistician who has this theory which says that you could use algebraic geometry to understand statistical models. Are you interested? And then I naively said yes. and then the first homework I got was blow up this singularity by pen and paper. And then my second homework was do this in a software like Singular or Macaulay 2, right? And that was my introduction to the field. And I think Bernd was a really good advisor. He's taught me a lot. And most importantly, he handed me off to Matthias and Sumio, who were both statisticians. And from the two of them, I learned even more about SLT from them. And I'm very grateful to them. And then in 2011, after having worked in SLT for a while, I realized that the key was KL divergence, that if you could relate anything to KL divergence, you then understand everything else. You could understand the generalization error, you can understand asymptotic behaviors, you could think about the zeta functions, you can do all kinds of things once you have the relative information. Then this is when I started working with Chris Hiller. I think, Chris, where are you? Just came here. Yeah, Chris is sitting over there. So Chris is a long-time friend, collaborator, and we had the same advisor, Bernd. That's how we knew each other. Chris was telling me, hey, you have to think about neural networks. We have to understand what's really going on in our minds. And he had these fascinating ideas, and he got me hooked. And at the time, I think we both knew deep learning was not the answer. We knew there was something more. And I wanted to understand neural networks, deep or not deep, spiking or not spiking, using relative information. And so I then went back to Singapore, and I spent a few years there. One of the things that I think I remember the most was AlphaGo, when we were able to use a neural network to defeat the best Go players in the world. And then I think it was at the time I realized that if we wanted to get neural networks to do anything of significance, we have to provide some kind of alignment to the neural network. And here I mean alignment more in a naive sense that I was thinking of back then, which was that you have to provide guardrails. You have to actually help it to find the right answer. And so And so, for instance, if I'm driving and I on the road and I'm not able to see, I'm blind. What can I do, right? So well, I can either stop driving and just wait on the road and do nothing, or I can say I roughly know that this is where I want to go to, and I'm just going to drive there as fast as I can, and I'm just going to ignore anything that comes along the way. So you either go broke, as in your car breaks down, or you go brute and you just go all the way. And realize that if you're an AI that's trying to accomplish a task and you don't provide any kind of handrails or guards or alignment, it's literally either going to not learn anything and go broke, or it's going to go brute and all the way and just brute force its way to the solution. And so I started thinking about how we can provide some kind of alignment to neural networks. And that's how I ended up thinking about dependent type theory and proof assistance. In a proof assistant, the way that you will prove a math theorem is that you will provide the math theorem to the computer as a goal, and the computer would then assist you in finding the proof of that theorem by a series of steps or tactics or logical steps. Okay, and along the way, the program will tell you that that's not a logical step, or you're getting further away from the proof, but essentially you will get there with this guide, with this alignment. And so I became very interested in type theory and then eventually category theory. And that's when I realized that information is constructive. That if you look at the way that the KL divergence is built, most of us will think of KL divergence as the integral of Q log Q over P. But the truth is, information KL divergence, that's not actually the most natural way to define a KL divergence. The most natural way is to say, what happens if you take the product of two distributions? What happens to a KL divergence? Or if you take the disjoint union of two distributions, what happens? And if you keep building up information this way, you will find the KL divergence that you need without evaluating a single logarithm or integral. And so when I heard Dan talk about his laws of universality, this is what I was thinking about, that because data is constructed in nature, and therefore when we understand that, it would also have to be constructed in such a way. And so I started thinking about information in a more constructive way, and this is how I ended up working on category theory and information cohomology, and this is also work with Chris. So today, I'm going to talk about two projects. The first project is information cohomology, which is with Chris Hiller and also with Tai Dene Bradley. The second is on spiking neural networks. Okay, this is work with Chris Hiller and Sarah Mazen from Claremont College nearby. And third, I'm also very interested in program synthesis, but I'm not going to talk about that today. To me, that's about doing inference with alignment. And there, yes?
Tomorrow.
Yeah, maybe tomorrow. I have to cancel my trip to Singapore. I'm also very passionate about this. So if you get me talking, I will probably not stop. But here we are looking at, for instance, creating domain-specific languages for large language models and reinforcement learners. We're looking at new kinds of proof assistance and tactics, new kinds of tactics, and then we're looking at how we can generalize over different kinds of types into this thing called type classes, and working with tactics over type classes. So I'll make a small plug here. By the way, I'm now director of research at Topos Institute, and we are hiring. So if you're interested in working on any of these projects, come talk to me, okay? Or email me. So I stole this picture from Jesse. Thank you. This is, I think, the picture or the idea that got me hooked on SLT. Okay, is this idea that if you start off with the density of states, okay, state density function, and the state density is a measure of the volume of level sets of the KL divergence of relative information. Okay, so if you have, let's say, a certain value E for your KL divergence, you could look at all points in your parameter space that gives you that value of KL divergence. And you could ask, what is the density given by that level set? That's V of E. Okay, so it's a distribution. V of E is a distribution over all the energies. You could apply a Laplace transform and you get the partition function or the marginal likelihood or the free energy, or you can apply the Mellin transform and you get the zeta function. And by switching between these three things, you can understand a lot about statistical models. And this is the reason why I got into SLT, because I realized that being able to put on different hats to understand statistical models was very, very important. Okay, so now I'm going to put on some of those hats and think about spiking neural networks. And what I'm about to say is an outline. Okay, I could probably talk about spiking neural networks for 2 hours, but I basically kind of took down what I think are the most important things, which I think will be useful for studying spiking neural networks. And so yeah, please feel free to ask me more questions later on if things are kind of hard. By the way, you are also welcome to ask questions along the way if you are doing the talk. If you have something that's not clear, please ask. So let me start with the setup. Okay, so I'm not talking about neural networks in general. I'm just going to talk about a statistical model just in general. Okay, in statistical learning, yes.
I just have a preliminary question before you.
Yeah.
Are we going to be talking about purposes?
No.
Thank you.
No, unfortunately, no. But I will. I'm trying to keep most of the technical details out. Yeah, out of this. Good question. So statistical learning. Okay, I want to start with something familiar. So generally, I'm thinking of a situation where we have an observed variable x, and we have maybe a hidden variable z, and we have a true distribution q of x, which we don't know, and we have some model of the joint distribution between x and z, okay, which is parameterized by some parameter theta. And for now, I'm going to assume that if you integrate out z, you get the marginal distribution on x. So the goal in many statistical learning problems is to find the theta that minimizes the KL divergence between q and p theta of the observables x, okay, which is the integral q log q over p. Now, because we have a hidden variable z, the usual trick is to use tools from a tool known as variational inference. And the trick is to introduce a variable, a distribution q of z given x as an extra parameter for optimization. So you expand the scope of your optimization. You have, so because of q, you're given that distribution q of z given x, you then have the something I call the discriminative distribution q of x and z, which is the product of the discriminator with q of x. And I also have the generative distribution, which is the joint distribution. And often the joint distribution is written as p of x given z times p of z, some prior on the hidden variable z. And then we changed the problem to be about minimizing the KL divergence between q and p theta on x and z on the joint. Okay, and we do that by alternatingly varying q while holding p theta fixed, or varying p theta while holding q fixed. Okay, so there's some kind of a two-step algorithm in here, and because of this two-step, there are a few variants of this variational inference algorithm. One is called the EM algorithm, or expectation maximization algorithm, from Dempster, Laird, and Rubin. And there, they let q of x given z be the posterior p of z given, q of z given x be the posterior p of z given x at each step of the optimization. So you let q be the posterior at the first step, and the second step you then optimize over p, over theta. There's a different variant that not many people know, is by Amari. Amari is a brilliant guy who does a lot of work in math and neuroscience. It's also called the EM algorithm, but E here stands for exponential and M stands for mixture. And here you let q of z given x be parameterized. You introduce some parameter lambda, and you let q of z given x be some model, and then you optimize between lambda and theta. So it's a bit more general than the usual classical EM, but I like that because Amari's EM algorithm, it feels more biologically plausible than the classical EM, because Bayesian inversion, which is assumed in the classical EM, okay, is hard. I actually highly doubt that biological systems can actually do that inversion in our heads. But I would think that it does some approximate inversion with some model like Q lambda. So that's actually the trick we're going to be using with spiking networks. Okay, so now I'm going to introduce the model for spiking networks. In terms of, I'm going to first assume that I'm going to work in discrete time. Okay, that is a very bad approximation because the spiking networks I'm looking at are continuous time models. But for the sake of today's talk, I find that it's going to be easier to talk about things in discrete time. And then you can come bug me about continuous time later on. The concepts are very similar. Next, I'm going to assume that the environment is encoded in these variables x1, x2, and so on. So x1 will be the state of the environment at time 1. I assume that the environment is immutable, so we are not able to do actions to change the environment. I'm just an observer of the environment. And possibly some parts of x is hidden from me. Okay, and that's going to be okay. And then last, I have these memory variables, which I call z, z1, z2, that gives me the state of the neural network at each time. And now I assume this memory is mutable in the sense that we are able to change the state, store things in the state. But we do not want to think of these as latent or hidden variables. They do not in any way represent what's hidden or latent in the environment. These are just memory variables to help us keep track or account for things. So then the goal, the high level goal is that we want to optimize the use of this limited memory for predicting the environment. So you can imagine, for instance, a naive thing to do is just to take the axis that you see and you store it into Z. But there's only so much you can store in memory. And then you're going to run out of memory. So is that the most optimal way to use memory to predict the future of the environment? Okay, that's the thing that we're trying to solve. And so I'm going to make it a bit more explicit. The goal for me is to minimize the KL divergence between x, the time series x1 to t, and z1 to t. Okay, I'm going to look at those two, all the variables over time of x and z. And I'm going to look at the KL divergence between the truth, which is q, and p theta, which is my model. And then I'm going to divide that by the time horizon, because this information measure goes pretty big over time. You want to keep it kind of somewhat finite. So we divide by t and we take the limit as t goes to infinity. That is my objective. Okay, so the nice thing about the EM algorithm, Amari's EM algorithm, is that I can actually put constraints on my Q, my discriminative distribution Q. So in general, if you do not have any constraints on Q, you can think of Q as a product of zk plus 1 given z1 to zk, and then given the entire environment. So you can do this with any distribution. Any distribution like this can be written in this form. Okay. So that's the most general structure I can have for the discriminator. Now, for simplicity, I'm going to say P star is the optimal distribution I get from minimizing this KL divergence, relative information. So in the simple case where there are no constraints on Q, you will find that the optimal KL divergence we get, which I call I free as in no constraints, not free energy, okay, is just the KL divergence on the observables, X. You can prove this. We can prove this by setting Q to be exactly the posterior on the axis, and then you'll get this value for the optimal information. Or you can have something that I call the online learning constraint, which is that the Q at Z time k plus 1 must only depend on the axis up to time k. So the only thing I've changed from up here is that I've changed the time horizon from t to k. And in that case, I also get a number, and that number I'm going to call I online. And because there's a constraint now on Q, I online is going to be strictly is going to be bigger or equal to I free. And then lastly, I could say that I'm only going to look at not the entire trace of the history of my memory and the environment, but only at the most recent one. So I call this limited memory. Okay, so I don't have a memory of the entire history of the universe. And in this case, I'm also going to get a new kind of information bound, which is called IMEM, which is larger than I online. And so the reason I'm doing this is I'm trying to say that if you have certain constraints on the kind of Qs that you have, it will also put a constraint on what kind of learning algorithm you can get. In terms of a neural network that has online learning and limited memory, this is the best you can do. You cannot do any better than this. If you want to do better than IMEM, you're going to have some kind of prophetic knowledge of the future or infinite amount of memory. Okay, but these put some information bounds on this. And now what I'm going to do next is I'm going to try to attain this bound, IMEM. Okay, so we're going to assume limited memory. So I have a Markov process in discrete time given by this product, this factorization. I'm going to assume that this Q distribution on X and Z, it has a stationary distribution. Okay, this is a very big assumption. Okay, so it will likely put some constraints on IMEM. But I assume that the true distribution is somewhat stable. It's not changing all the time. And I'm going to have a notation Q bar. So Q bar is the same Markov process as Q, except that the initial distribution is now pi bar. Okay, so I take away the initial distribution of Q and replace it with pi bar. This is what Q bar is. So it's some kind of like long-term distribution of Q. You can think of it as a long-term distribution of Q. Okay, then this was my objective. I was trying to minimize this. And by using Kingman's sub-additive ergodic theory and under some mild regularity conditions on the stationarity of the distribution, you can prove that this is equal to some conditional relative information from Z2, X2, of Z2, X2 given Z1, X1 of this Q bar from P. All right, so it's a one step in the Markov chain at that stationary distribution. So that makes sense, like common sense wise, that this average of the KL divergence should be equal to the one step KL divergence. In spiking neural networks, you will want to look at the continuous case. In continuous time, you get something different, slightly different. You will be looking at the infinitesimal KL divergence. All right, so x1 to x1 plus t as when t goes to 0, and we want to take the derivative of that. Yes, Jesse.
Is this formula in the middle analogous to the expectation of the generalization error being related to time derivative in number of samples of the energy?
I'm not sure. I think it might be related. Yeah. In the sense that I think maybe both of them depend on Kingman's ergodic theory. But other than that, I'm not very sure.
So are you in similar say, or what is the sub-additivity?
Kingman has this theory of sub-additive processes, and then using that he can prove certain results like this. Just ergodic, yeah. So I'm assuming ergodic here. That my time series, my models are ergodic, and my true distribution is also ergodic. Okay, so now I'm going to apply the trick, the variational inference trick that I mentioned earlier. I'm going to now alternate between optimizing for Q while holding P fixed and vice versa. So, okay, as just a reminder, the setup is that I have now these two parametric models. I have the Q lambda model. I have of Z given Zn plus 1 given Zn and Xn. And I also have my model, which is the P theta model of Zn plus 1, Xn plus 1 given Zn and Xn. And my goal is to minimize this one-step KL divergence, one-step relative information, or conditional relative information. And you can do a stochastic approximation, use some kind of stochastic gradient descent to solve this optimization problem. But I call this stochastic approximation because of this. I'm actually going to sample. Is there a question? Okay. I'm actually going to sample, okay, well, the environment. I'm going to take a new observation from environment. And I'm also now going to sample Z. Okay. So instead of just feeding the entire distribution of Z into my next step, I'm going to just take one sample from Z. So this is why this is called stochastic approximation and not stochastic gradient. because I'm doing some sampling with the states and not just with the gradients. Then with the gradients, I'm going to compute the gradient of the generator or gradient for P. That's holding Q fixed and then optimizing for P. And then I'm going to compute the gradient for Q while holding P fixed. And then this is crucial. At the last step, I update both theta and lambda and repeat until convergence. So Susan, I was talking to you earlier. In classical EM, you update lambda in this step, and then you update theta in the next step using the updated lambda. But from my experiments and in trying to prove things, it was easier to update everything at the end in one step than to update individually. It makes the proofs a lot easier. Okay, so this is how we train a spiking neural network, and let's see how it works out. Okay, so the interesting things happens in step 3 and 4 of this algorithm. So in step 3, nothing very unusual happens. This is the usual log likelihood that we see evaluated at my data, and then I'm just taking the gradient of that log likelihood. So this is the usual gradient that we see in machine learning or deep learning. The interesting part is actually with the discriminator. So when we actually try to take the derivative of this with respect to P, with respect to Q, not only do you have to integrate under the integral of Q log Q over P, but you also have a dependency on the initial distribution Q bar. So that makes this very hard to differentiate. And one way to do this is to expand Q bar out into an infinite chain. And then once you do that, you will find that you get not only the usual log derivative term that you see over here, but you also have this infinite long sum of Q lambda terms that comes from this chain, this dependency on the stationary distribution here, Q bar, okay, which is not usually there in deep learning. And this is the interesting part, okay? The interesting part is that this, we can think of it as momentum, okay, a kind of momentum. And this, we can think of surprise, how different the model is from truth, because it's the difference between Q and P. And the reason I call this momentum is because, yeah, I'll get into that later. Okay, and so this is the update for the discriminator. It has two parts. It has the momentum and the surprise, and you multiply them together. And typically, if you try to do this in experiments, you will get very bad numerical behavior. So that's what I found out the hard way. So what you then try to do is you put a little bit of a discount in front, which is a beta term, and then this momentum term becomes more stable because you're now depending you're trying to reduce the weight of the past updates over if they're further back in time. Okay, so you do get the numerical stability, but one of the things that you lose is that you're not going to converge to the true distribution. You're not going to get true convergence. Okay, but it's not too bad. It's a small trade-off, but I think, in my opinion, it's a good trade-off.
The phase T minus I. So
yeah.
Where is the sum? How does that happen?
So this is the sum here, and you multiply right in front of this log derivative of the log term, beta to the T minus I. So when I is close to T, then beta T minus I is small. It's large. It's close to 1. But when I is small, like I equals 1, then this term becomes very, very small. Yeah. Chris. Yes, you're right. You're right. It does have a relationship in that. In fact, that's my next. So this is actually, you can think of this. T-gammon is a kind of reinforcement learning algorithm, and you can, if you look at this, you can see this is exactly the same as reinforcement learning, but with surprise as a reward. This is surprise, okay, and having discounted rewards. So it's exactly the same. If you look at this paper, for instance, if you fill in surprise as a reward, you literally get this as algorithm. So what is happening in here? We're training spiking networks with reinforcement learning. And the thing is that we didn't try to use reinforcement learning from the start. We just started with something that was very basic, which was the KL divergence, relative information. We expanded out the EM algorithm for that, and then we got reinforcement learning.
Could you explain what this has to do with spiking neural networks specifically?
Yes. That's my last slide for this. Yeah, so that was in discrete time. And now if you want to go to spiking neural networks, okay, the short answer is that you can go to this link on my blog, and I booked out all the details there in full glory. It's very messy, but it's there. But I would say that the main concepts are whatever I just told you. EM algorithm with this discriminator, and then working with these two models, and then getting momentum and getting surprise. So but some things are different. So the thing is different, that's different is number one, of course, we're working in continuous time. The second is that instead of optimizing the relative information, the conditional relative information, we're using relative information rate. And what's that? That was the thing that I showed you here, this derivative over here. So it's a derivative of the KL divergence. And even the relative information rate is a very beautiful object. So Chris and I have been looking at this for quite a few years now. I think it's really beautiful stuff. And third, it turns out that many different kinds of spiking neural models are possible. There are many different spiking networks that we could design, but they will all have very similar behavior. The main things that I think are important that we have in all these models is that number one, these neuron spikes are described as Poisson processes controlled by the cell potential. So the cell potential affects the rate of Poisson spiking. Second, the potentials, they will increase with each incoming spike, and they reset with outgoing spikes. Okay, this also is a crucial part of for the models to succeed. And third, the cell potentials have certain, the potentials are in each synapse. The synapse is a connection between two neurons, just as the weights in deep learning are the weights between neurons, right? It turns out that you have to use something called, you have to do credit assignment. That tells you how much to update the weight of that synapse given the spikes in time. Like spikes from a long time ago shouldn't have a big influence on the weight update. Okay, so you need some kind of credit assignment to decay with time. I can go into details about that if you guys are interested, but this is quite important for stability. Other than that, everything is free. You can change your models around. You can talk about how the potentials increase and so on. But these, I think, are the three most important things about getting the spiking networks to work. Jesse? Oh, yeah. So in a spiking network, you assume that you have a random variable x that is that's varying with time, continuous time. At each point of time, the neuron is either at rest or it has just gone through a spike event. So you get a delta in there. But otherwise, after each delta, it goes back to just being at rest. Yeah, before it spikes again. So you get these, you basically, if you drew out the time series of this neuron, you get a straight line, but with individual delta events.
In the original setup, the ZIs,
the ZIs will also be spiking neurons. Yeah, and so for instance, one way that people model this in formally is that for each variable x, I have a counter. So I have a step function where at time 0, the count of number of spikes is 0. It stays at 0, and then the first spike happens, it jumps to 1. And then after that, it stays at 1 for a while, and then the count will jump to 2 at the next spike, and so on. And then you model the wait time in between these two jumps in the counts as some exponential distribution that depends on some exponential rate.
Is this actually like a kind of network with like a significant amount of width and depth, or is
yes, yeah, it would be a network with quite a lot of connections. It kind of looks a lot like this picture here, where you have lots of interconnects within axes, lots of interconnects within the z's, and lots of interconnects between the x and z's. Yeah, but each of this represents millions and millions of synaptic connections.
These are like perception neurons and processing neurons?
Yeah, that's right, exactly. So these neurons, I think of them as having information being fed to them. So their states are not mutable. But these memory neurons deep inside our heads, we can they are allowed to have their states changed to remember things. Yeah, that's a simple way of saying it.
Also, like me changing my gaze to something else. Like
So now you are, yeah, so that's that situation where we change the environment or change the data that's coming in is not covered in this case. Yeah. Yes.
Just trying to understand how what you've been saying maps or is the setup you have in your network, you now provide some sort of input, you run it with key steps until it, let's say, settles down,
Mhm.
you take the output, and then this policy gradient style thing is essentially your loss. And then you still have to do, I don't know, heavy learning or whatever it is to update your actual spiking on the weights. And you just repeat the spread samples or
Yeah, so I assume that the habit learning that you're talking about is happening as the data is coming in. So it's not given in a batch form and then trained. And then the habit learning steps are precisely, in fact, going to be from sorry, I'm going backwards in time. From here. In fact, if you unpack these two steps, you will, in fact, get something pretty interesting, which is my next point. It turns out that this stochastic approximation algorithm explains the triplet rule in spike timing dependent plasticity. This is not published yet, Chris. We need to write a paper like this. But yeah, it will explain that. It's not just the usual STDP, but it actually explains the triplet rule. Yeah.
what's the triplet rule?
Oh, I actually don't remember the details, but it's kind of like in traditional spike STDP, the update to the weight of a synapse depends on the timing in between the post-synaptic spike and the pre-synaptic spike. So you have a synapse and it has two neurons. A spike in the neuron after the synapse is called the postsynaptic neuron. The neuron that's before that synapse is called the presynaptic neuron. And then they are spikes. So if they spike together, the weight will go up. But how much it goes up depends on how far apart those two spikes are. And sometimes you could even have the negative effect. Yeah, where the weights go down. So the triplet rule is an even more complicated way of saying that. And in my opinion, there's no triplet rule in biology. It's just stochastic approximation. And then the triplet rule is a consequence of that. Or what we see in nature is just a consequence of that. Okay. The second thing is that the surprise term in the discriminator seems to explain dopamine-based neuromodulation. So it turns out that we know that there's some long-term effects of dopamine on memory, and it seems like it seems to me that would explain how this measurement of surprise is happening over time. When you get surprised, you get lots of dopamine. There's a big change in the learning. And then lastly, this momentum term, if you try to do it right in the neural network, it seems to me so far to explain something called neuronal adaptation. Okay, I'm not going to go into details, I'm sorry, and refractoriness. And so for the people who know neuroscience in the crowd, okay, I think that these two things are actually directly coming out of the momentum term in the updates. Okay.
But you introduced this kind of arbitrary.
Sorry?
Like you had to introduce this kind of arbitrary.
Yes. So if I did not introduce the discount, this is a numerically unstable algorithm. Okay. The discount is something that it seems like a natural thing to do, because if you think about why it's unstable, it's because things in the past are still affecting things in the future, no matter what the time gap is. So the discount is a very natural thing to add, but just by adding that little bit of discount and then trying to think about how a biological system like a neuron will implement that discount, it means that you have to have new kinds of weights in there which are decaying with time. That's exactly what's going on with adaptation. Adaptation has certain new numbers which are decaying with time, and I think it's because it's trying to take into account momentum. And I can give you a little piece of code that actually shows that adaptation comes from momentum. It's a Python script. Python script.
This Q lambda can be whatever it wants to be. So, I mean, isn't this beta thing just like a temperature almost? You can just put it into the lambda.
Oh, Yeah, it's not that unnatural. Yeah, that's right. It's not temperature though. It's slightly different from temperature. But that's another interesting question. Where's temperature coming here? But I'll not talk about that. Yeah, but this idea that there is a Q network and a P network is not new in neuroscience. I think Feister has talked about this in 2016. This idea of a Q network and P network, two different networks going on in the brain. So I'm not the first to suggest this relationship.
Also like traditional models that definitely like just having RL rather than one building level. But then does that also incorporate this idea of having a QT to later generate as part of the dopaminergic system? Or is that like new to like that?
I think in the sense that yeah, it's not new. So the relationship between surprise and dopamine, or surprise as a reward, I think this is long known. So the connection that I'm saying here is that this surprise is literally coming out of the EM algorithm. I did not have to call this term surprise, but I'm calling it surprise now, and that's the connection I'm making. And so that would explain dopamine. Maybe, I don't know. These are very speculative. So a lot more work needs to be put into these two things here. But that's my hunch. Okay. I would like to go on to the next part of my talk. Okay. So I'm making a big jump here. We're going to talk about cohomology, which I think maybe Dan, you'll find this very interesting. Because the reason I'm talking about this is because you gave a talk on the principles they've highlighted, and I see a lot of those principles being tied back to cohomology.
Before I have even more to think about, can I ask in the first part? So, what about this? I mean, this is phrased in a way that doesn't really require SLT. At the same time, it's natural to speculate about the role of singularities in the brain, and Watanabe has a nice line in his book about it. Please speculate.
Okay, I actually had this discussion with Susan just now, but any understanding of SGD, the relationship SGD and SLT, has to go through variational inference. So I want to think about even if you are just updating not a time series model but a static model, a deep neural network, I would take a snapshot of the model during training. So the parameters at time t, the data that I'm feeding into it at time t, versus the parameters at time t+1 and the data I'm feeding at time t+1, the batch that I'm feeding in. So I think of even a static model as a time series with gradients being updated and states being updated. So there is a stochastic approximation algorithm at work. There is an analysis of the convergence of this stochastic gradient algorithm. And traditionally, in understanding stochastic approximation, you have to look at Poisson equations. You look at ODEs, the continuous time version of that discrete time process. You have to look at Lyapunov functions. And I think when we think about SGD from that lens, I think that the singularities of the KL divergence and its effect on SGD will become clear. So that's my hunch. And so coming back to this, spiking neural networks, I think there's a lot of SLT at work here that I don't understand. It's basically affecting directly the SGD through the Poisson equations, through the eigenvalues of the Poisson equations.
So your proof technique of the versions of the exponential algorithm uses these.
Yes, it doesn't use the singularities; it just uses behaviors of the Poisson equations and so on. I want to know what's the relationship between the Poisson equations and SL and the singularities. I haven't thought about that. Yeah. So okay. Now I'll try to be brief about this. Information cohomology. And so let me talk about why I'm doing this. So I go back to Jesse's picture, which I think is to me the most important picture in SLT. And I say, how can I use this to understand information in a more general case? Is KL divergence the only way to talk about information? Is there other kinds of information, for instance, in quantum systems, when we don't have locality, when Bell's inequality gets violated? And then it's hard to talk about KL divergence in that case. Can we come up with a more general kind of information, which we can then look at its Fourier transform and its Laplace transform, and then understand what's going on in that quantum system or what's going on in that system. And the word I want to use here is topos. So there is a topos. There's a topos in here, and I want to say what is the information, relative information or KL divergence of that topos. That is the and I think that's, and if we can do that, we can use all these different tools in this triangle to understanding that topos.
Relative information of two different toposes to each other?
No, it will, yes, maybe not clear yet, but I will get to that. The answer is I don't know.
Topos is too hard to understand already.
Yeah. So I'll start with something simpler. Okay. I won't talk about topos today. So first, I'm going to think about measures and not probabilities. I just want to think about measures. I want to think about KL divergence between two measures. Okay. So then if I'm trying to compare a model measure with a true measure, I want to think of it as the comparison as a functor between some category P, which I call the model, and some category Q, which I call the truth. And these are categories of what I call weighted contexts and substitutions, which I'll explain in a bit. This is a big picture. So I have a functor between categories, right? I'm trying to take P, which is my model, and trying to represent that in Q, trying to find semantics in Q, which is reality. And I'm asking what is the information content of F. So I want to have a measure of how good F is at modeling truth for each morphism, for each connection that I have in P, or for each conditional relationship I have in P. What is the KL divergence there? And I'm going to define the KL divergence as a functor from P to, oh, question, yeah.
Why can you choose to model, have your model and truth be a category? Like what's
okay, I will get to that soon.
Okay.
So this is the overview so that it won't get too confusing. Yeah, thanks for that question. So I'm going to define KL divergence as a functor from P to R. And what's R? R is the category of dual numbers. This is the deformation algebra. Dual numbers, I'll tell you what it is in a bit. It's basically numbers with some infinitesimals. The real numbers with some infinitesimals. And then lastly, okay, I'm now going to define some algebra where I have for each morphism I have in my model, I'm going to define a small little category, okay, that contains just F. And then I'm going to think of these functors to the duals as forming some kind of algebra. Okay, you can multiply these functors together. You can add them together. They form an algebra. And then it turns out that the derivations of this algebra is precisely generated by KL divergence. So KL divergence is measuring holes in this algebra. Holes in how we measure morphisms. Yeah, this is a one morphism category. I don't have a nicer way to do that. There probably is a nicer way, but this is the only way I could think of right now. But yeah. So let's.
What are the morphisms again?
I'm gonna go through that now. So this is the big picture. Okay, now I'm gonna go slowly now. Okay, unpack what I said in those slides. So now assume that I have two measures on a finite set X. Okay, and I'm going to assume that they have, okay, so suppose P and Q are two measures on a finite set, and they have the same total measure. And let's say that pi is a measure preserving map. Okay, it means that I can actually define some kind of conditional, okay, so that the measure at Y is given by this conditional times the measure at X, and these conditionals sum to 1. That's my definition of measure preserving. But maybe in your head you're thinking of a more obvious one, which is that and the measure of the image is the same as the measure of the the measure of each point in X is same as the measure of the pre-image, right? That's also another way to think about it. But this I prefer to define it this way because next I'm going to define the relative information as of this morphism as the sum over the distribution, the true distribution at X on X multiply by the KL divergence between Q, Y given, or Q of Y given X log Q of Y given X over P of Y given X. Okay, so those who have done KL divergence before, this is quite well known in statistics, except that now these measures, they don't sum to 1. And they still behave like KL divergence. So this is the KL divergence between two measures. Now I'm going to talk about my categories P and Q.
Some kind of relative function.
Relative.
It's relative to a map.
Yeah.
You are building the relative.
Right. Relative to this map F. Yeah. So now I'm going to talk about my categories P and Q. So in those categories, the objects are called contexts, and those contexts are just finite sets. So in P, finite set, I have finite sets as objects. A morphism in the category is called a substitution, and a substitution is a set map, okay, from Y to X. So note the reversal of the arrows, together with conditional probabilities, which I defined just now, such that the conditional is equal to 0 if pi of Y is not equal to X, okay, and that all the conditionals sum to 1. So so what you saw in the previous slide with the conditionals, now imagine that's this conditional give me maps between the finite sets. Two substitutions compose, if I compose the underlying set maps here, and I multiply the underlying conditionals, right? So far so good. So if you're confused by this, just think about statistics where X and Y are random variables, and that the maps are conditional probabilities between random variables. And then for each context, there's an identity substitution where the conditional is equal to 1. Okay. And then lastly, I have a trivial context, which is, sorry. So with these 4 things, I have a category, the first 4. I have a category. A category is like a group or a ring. It's just an algebraic way of organizing information. So lastly, I'm going to define a trivial context as a context that just has 1 element. Okay, and so any substitution from the trivial context to X would give, the conditionals are basically going to give you probabilities on X. Now, I could have many different trivial contexts, all with different measures.
Most of this, I guess, also works for Borelian measures, right? Topological spaces with
Yes.
Borelian and proper map, right?
I think so. Beyond like finite maps and so on, I think so. So I'm more interested in the categorical structure of the maps than the what actually the objects or morphisms are. I have 2 minutes left, and I'm wondering if I should try to wrap up, or I should go over time. Okay, thanks. Okay, I'll try to be fast. Okay, so that was context and substitutions. Now I want to talk about weighted context and weighted substitutions. So the only thing I'm adding is that for each of those finite sets, I'm going to add a measure. And a weighted context is the context of the measure. Weighted substitution is a substitution that's measure preserving. So if you take the conditionals and you multiply it by the measure, you get the measure on X, then you get a measure on Y. Okay. So now I just throw measures into the mix. Now with these weighted contexts, I have 2 more things for free. The first thing that I can do is I can add them. So the addition of weighted context is the disjoint union of the underlying sets and measures. Okay, and you can check that this addition of weighted measures also carries over the substitutions. You can take 2 morphisms, and you can, if you take the disjoint union of the underlying maps and conditionals, you will get something that is again a conditional. You get the underlying set maps and conditionals make it an actual morphism. So you can actually, this is a valid operation on morphisms. And then the next thing I can do is I can take products of weighted contexts. The product is the product of the underlying sets and measures. So you have product measures on product of sets. And the morphisms can also multiply together. You have to check, but the products of conditionals again are conditional. They sum up to 1, for instance. Okay, so I have a nice. Not only do I have a categorical structure on this, I have a a bimonoidal structure on my category. So these are called rig categories, RIG, like a ring but without negative. So it's RIG, rig categories, bimonoidal categories. And the sums and the products, they distribute over each other. Okay, now I'm going to define the dual numbers. All right, so the dual numbers is also a rig. Okay, first you look at all the non-negative real numbers, and you append an abstract variable called epsilon, and then you mod out by the ideal epsilon squared. This means that all the numbers you have are form a plus b epsilon. But if you multiply them together and you get epsilon squared, you just assume it goes to 0. It is 0. So it's like real numbers with infinitesimals. Now to show the relationships better, I'm going to call addition in the rig in this duals. I'm going to use O plus, and multiplication in the rig. Sorry, in the duals, I'm going to call it O times. Okay, tensor product. Think of it as a tensor product. In information theory, we sometimes want to work with extended duals. So we add infinity to the real numbers. Okay, and then you can kind of make everything work well. If you have anything added to infinity is again infinity, and anything multiplied infinity is infinity except for 0. You get 0. So, yeah.
The extended duals are non-associative?
They are
Infinity times epsilon times epsilon.
That's a good question. I think it should be, but
Or do you just not allow multiplication by epsilon?
I need to think about that. Yeah. Okay, let's come back to it in a while. That's a good point. Okay, so sometimes we could be using the extended duals, and then now I want to think of the duals not just as a rig, but actually as a category, a rig category, where the objects are real numbers and the morphisms are also real numbers. So if you sorry? Yeah. No, sorry. These are reals, but they're not duals. So the objects are just the usual real numbers without epsilon. And then the morphisms are supposed to represent the coefficients of epsilon. Yeah. So now you can think of the duals as a category. So the morphisms are only between each object and itself. So you have these loops, right? So each real number is an object, and then all of the epsilon infinitesimals are all morphisms on that object, the loops.
Essentially, trying to replicate the categorical level scale divergence.
Yes, it is. Yeah, it is the tangent structure. Yeah.
There's a notion of a tangent structure on a category. We try and think of a category as having something like a Jacobian that maps a manifold to its tangent manifold. Probability in information theory is in the tail divergence as being an infinitesimal metric on a space of probability distributions. So Shaowei is basically explaining the categorical. Or even just algebraically, then you can think of adjoining epsilon and then modding out by epsilon squared as kind of adding a tangent to a ring. Yeah, that's right. Yeah. So
Yeah.
We construct tangent structures often by mapping.
Yeah, and I'll come back to the tangent structure in a bit. In fact, yeah, that was a really good comment. Thanks. So now you can check that this addition and multiplication for the duals now extend into this category. We can do that for the objects and the morphisms. It works out correctly. In fact, if we now think of the product of two morphisms B and D, where B is from A to A and D is from C to C, then you are going to get that A, you're going to get the real number, the morphism you're going to get is the real number A times D plus B times C. Okay, so it has this very strange multiplication on the tangent planes, which is something that we should expect when working with the tangent planes. Okay, so if you think this is, yeah. It will become clearer in a bit why this is important. So those are the dual numbers, the category of dual numbers. Okay. So now I'm going to try to build a bridge between the rig categories that we have with the random variables, the measures, and then the rig category of duals. Right. So information category is a rig category, okay, of weighted context and substitutions. So think of the information category as a joint distribution on a collection of random variables. That's the way I think of an information category. So P is going to be some joint distribution, and Q is going to be another joint distribution. And so I have, when I'm thinking of two different rig categories, I have two different distributions that I'm comparing. So given two different information categories, we are going to compare them by a functor. And what do I mean by this? It means that for every object in P, I'm going to try to map it to some object in Q. That's what we're doing when we're comparing stuff. But that's somehow subconscious when we write that Q and X and P and X are the same X. But to do it formally, you have to introduce this map relationship between the objects and the morphisms. Okay, and then
This is the thing that says the two X's in the tail of the F is. Otherwise, you don't know what the.
yeah, which X you're talking about, right? Yeah. So this functor makes that very clear or formal. Then for each, now I'm going to define this new function, okay, IF. So when IF is applied to an object X in P, I get a total measure at X. And because it's measure preserving, that's also the same as the total measure at Q. Sorry, the total measure of P at X is the same as the total measure of Q at X. Okay, that's oh, sorry, that's a requirement. Sorry, that's an assumption I'm making. So that's IF applied to an object. Now I could apply IF to a morphism. Then I'm going to define it to be this: the sum of Q over Q of X to the sum of Q of Y given X, Q of Y given X over Q of Y given X. This is the KL divergence. So this function on the objects and morphisms, I'm going to call it relative information. This is my definition of this relative information on the functor F with respect to the functor F. And it turns out later we're going to see that this is actually not just a function, but it's a functor. It's a functor. Okay. Relative information is a functor. So let's check this. Let's check that the function I defined just now is actually a functor from P to the dual numbers R. So first, let's check that on the objects. If we check that on the objects, because the morphisms in R are self-loops, then it turns out that therefore the source and the target of X and Y must be mapped to the same number A. And this means that that the total measure on X and total measure on Y is the same, which means that F is measure preserving. That's exactly what I said I had defined it to be at the beginning, measure preserving maps. Second, we have a sum rule, which is that the measures of disjoint unions are sums of measures. Okay. And then thirdly, product rule, measures of products of finite sets is the same as the product of the measures of the finite sets. Oh, okay. I'm going to talk about it in the next slide. Yeah.
How long do you still need?
Maybe 5 minutes. Is that I can? Okay. Okay. So next we have we need to check this statement. There is a functor on the morphisms. So first I have the chain rule. If I compose two conditionals, then I get the sum of the KL divergences. So this is like saying the information of X, Y given Z, and then Y given Z given X and Y, and then the KL divergence of Y given X. When you sum them together, you get this information on X, Y, and Z. Okay, so there's a compositionality that comes with the KL divergence. We also have a sum rule. So the KL divergence over disjoint unions is the sum of the KL divergence on each of the morphisms. And then the interesting part is this: we have a product of morphisms. Okay, we actually have this rule that the measure on X multiply the KL divergence plus the measure on F multiplied by the measure on X prime. So you can think of this as taking, let's say you take a convex combination of distributions. No, sorry. Okay. Yeah. So it turns out if you look at two different, if you look at the product measures on F and H and you work it out, this is what you get, the KL divergence. But the thing I want to highlight here is that this structure here is exactly the structure on the dual numbers that we saw earlier. This structure here. Okay, and so this is the tangent. This is the tangent category behavior that Dan was talking about. And then lastly, localization. If P equals to Q, then the KL divergence is 0. So this KL divergence IF is defined to be 0 at Q. So it's localized at Q, but not localized as in like localization that we think of in algebraic geometry. I couldn't find a better word, but maybe it is the same. I don't know. I need to think about that.
You want to divide that
No, we won't divide by that. So maybe, yeah, I don't mean that we want to localize that way. Yes. Yeah. So local, maybe local at Q, not localized at Q. Yeah. Sorry about that. This is what happens when you try to do this like 2 days before with very little sleep. But yeah, so this is my last slide. I think so far I've built up a lot of material, but what eventually, if you want to, we already have this tangent structure over here. We still need one more extra step to think of it as cohomology. And when you want to think about cohomology, you need to think what is the algebra that I'm taking cohomology of. So I'm using Hochschild's cohomology, and so there has to be an algebra involved. And it turns out the algebra in this case is the algebra of these functors from these very simple one morphism categories to the dual numbers. You can multiply morphisms, so you can multiply these functors together. It feels very ugly at this point. I'm not sure if this is the best way to do it, but the underlying algebra, if you look at the cohomology of that, you will get precisely KL divergence. Okay. I won't unpack this too much, but if you're interested, I can go through with you later. So my questions are, what are the higher order cocycles of this cohomology? Can we generalize this to other kinds of information categories like quantum categories? And lastly, what are the state densities, the Fourier transforms, the zeta functions, the Mellin transforms? What are they in this case? I think that will be very interesting to look at as well. Yeah, question?
Yeah, there is also like this information from homology that was defined by Diablo and then
Yes, that's right. Like, yeah. There's some difference. So here they look at entropy, whereas I'm looking at the relative entropy. Yes. Yeah, they do have that. It's one of the differences is that they don't look at dual numbers. And so I need to understand really the how theirs is connected to mine. But I have to say that a large motivation of all this is their paper. Okay. So this work is very, very highly inspired by their paper and also by Ty Dane Bradley's paper. So there's a lot of influence there. Yeah.
When you talk about the partial homology, you mean that degree or all degree?
Just the first degree. So at least for KL divergence, it's just the first degree, the first cocycle. The higher order cocycles, I don't know what they are actually. And yeah.
What happens if you dual line? So if you consider functors from the dual number category into your category P, you go backwards. So this could be like a cotangent structure. Does it have some meaning?
That's a good question. Yeah.
Yeah.
Get homology.
Then you can do a partial chain complex.
Yeah, I don't know. I haven't thought about it. But I think that's a really good question. Okay. Thank you, everyone. So I believe we're out of time for questions, right? So how would you like to?
Go there and wait. I have.
To look at SLT for quantum.
Oh.
So there is singularity structure in the core module. It's just, sorry, singularity structure, but you can't define the KL divergence even for some of these non-local quantum systems. So I don't know much about physics, but I think I was going in the direction of like Cochin Spectre. They have some results about contextuality in there, and it seems like there should be a way to apply SLT to that situation, and this is my approach attempt to do that.
Also, low cost.